this all set up. Well, I got this thing off of Amazon, I think for like 80 bucks Canadian. So we'll see how this thing pans out. Supposedly it is a 30 volt, 10 amp variable power supply. And I should probably turn my microphone up to somewhere around here, I think. Yeah, okay, hopefully that's more audible. I can go a little louder. Alright, so Uniroi power supply, Amazon, pretty basic box, nothing special there. Off camera I've got a linear power supply that I've had since, I want to say 15 to 20 years now. No, not 20 years. 15 years is pretty reasonable though. So I've had that power supply for 15 years and it's, it's still working. I just need a second voltage power supply handy at the same time. So, what do we got in the box? A couple leads, IEC power cable, more leads, and the power supply itself. This thing is light. This is scarily light. Instruction supply, and that's it. A single output, high precision. You're not getting that from Chinesium, but I'm fine with just the basics. I don't have an oscilloscope handy here, so I'm not sure I can really measure the voltage stability or the ripple, the current ripple. But, for 80 bucks Canadian, why not? Got some foam. That's the power supply. It's pretty basic. It is super basic. Oh, lordy. I'm not getting some good vibes already. This switch feels kind of cheap feeling. Got some binding posts. Current voltage adjust. Got a LED 7-segment indicator for voltage, current, and constant current, constant voltage mode. Got some rubber feet on the bottom, that's not bad. Actually comes with a fan, which also isn't bad. Preset for 115 volt, which is nice out of the box since we're in Kazakhstan. What voltage, or not voltage, what current fuse is this? Use only 250 volt fuse. This is a 250 volt, but how many amp fuse? This is a 3 amp fuse. So does that make sense? 3 amps at 120 is 360 watts. Yeah, that's okay. Alright, so I think I'm going to power this on first. And then I'm going to do some digging into it. I'm trying to think of a good way to... Yeah, that'll work. Show this off for the camera at the same time. It'll work in reverse. Alright. Not even bothering to get into the cables yet. Does this thing fire up? It fires up. Let's do that. There we go. So, I want my voltage adjust. Oh, right, my current's turned all the way down. Okie dokie. Let us set up ye old fluke and measure some voltage. Am I gonna be able to just like clip that in there? Probably not. Oh, that's handy. Now, interestingly, the fan is not constant. The fan on the back is not constant. It only seems to want to come on when it's needed. So, I guess when we get into the guts of it, we'll see. Alright, not too much glare on that multimeter. Let's start cranking up the voltage. This ain't gonna be easy. Oh, let's do course adjust first. Course voltage adjust. Fine voltage adjust. I believe my fluke multimeter more. Yeah, the 1-digit precision display on the voltage isn't too bad, I guess. But let's keep going with the voltage. Max it out at, oh yeah, you can actually just go a hair over 30. Alright, I'm trying to think of what I've got that's a decent enough load. What can I find that's a good enough load to simulate? You know what? This is probably less than a spectacular idea, but I've got this lovely heating element known as a cordless hot glue gun. This is into the hold my beer and watch this territory. You know what? Let's go back to this view, and I will shove you to the side as everything topples over. And then we'll put this over here as well. And that gives me just a hair enough space. Alright, what could possibly go wrong? I want to see how this thing handles under load. I'm going to reduce the voltage down to 18 volts. Oh, that's going to take some getting used to. I'm not used to the digital display. I'm a fan of the older analog style display. Which side's positive? That's got to be important. Let's find out. Alright, so I've got minus to here, positive to here. Yeah, that's okay. Let's just put a little plus sign so I don't reverse voltage this and toast it. These are some pretty anemic wires, and I do not like the feeling of that. They are molded. So yeah, maybe now's a good time to take a look at these leads that they give us, because they are awfully anemic. In fact, I will That's a little funny. They use a zip tie on one, but they use a twist tie on the other. And while we're at it, this IEC power cord is 0.75 millimeters squared copper, which when you convert it to AWG, let's do some cross-referencing. 0.75 millimeters squared is about equivalent to an 18 gauge wire. So this is cheap, but it's not insufficient for about 350 watts coming out of this thing. So far we're not into, you know, complete bad territory. Can I do this? This is so dodgy. Oh, this is very much dodgy. Alright, well, this is going to be interesting quickly. First, let's put the binding post back on. Alright. These are some very anemic wires, though. Yeah, actually, that's kind of surprising. That's not totally anemic. That looks like it's at least 18 gauge, which, I mean, for 30 volt, 10 amp, it's anemic, it'll get warm, but it's not going to catch fire, at least not for short-term usage. This is really not the way you should be doing this, but it's all I got right now. So let's see how this responds when I put it into a constant current situation. Alright, we're going to go constant current, and we're also going to want to monitor voltage as we go. So let's clip that on there, and let's clip that on there. And we're not drawing any power yet because I haven't turned on the hot glue gun. This is so dodgy. This is so dodgy. Okay, so I'm gonna just double sanity check that minus goes to minus and plus goes to plus. Yeah. Okay, contact. We are in constant current mode now, which means if I bump this up, we're drawing... Interesting. Current draw kind of ramps up as this thing gets warmed up. I mean, the emissivity of this thing is not going to be indicative because it's reflective. Yeah, I guess that's a funny quirk of these IR thermometers. The IR thermometers rely on blackbody radiation coming off the object, so in this case it is a hot glue gun, it's an aluminum and brass tip. You're not going to get very much blackbody radiation off of that. Kind of smelling electronic-y smells. That's a very qualitative term. voltage seems to be holding pretty steady. Current draw is slowly going down. Come to think of it, I think the lithium batteries, even though they're 18 volt nominal, the actual terminal voltage is a bit higher, so I'm going to bump this up. I also don't feel like waiting forever. Go with 19. And I can feel it getting warmer. It is working. I haven't been able to get the fan to kick in though yet. And of course, because it's negative temperature coefficient, it's going to reduce its current draw as it reaches its working temperature, so I may not be able to get a huge amount of simulated load out of this. But it definitely works. Alright, you know what? I think I'm going to turn this off. Definitely no fan action yet. Doesn't feel warm. And at least for 2 to 5 amps, yeah, these leads aren't that bad. These ones, on the other hand, they're very silicone flimsy feeling. The amount of copper in them looks like it's more like a 20 to 22 gauge. And there's already rust on some of these terminals coming out of the box, so that's not really encouraging in terms of quality control. That one's not rusted, but yeah. It's a little disappointing to see anemic leads coming in with these power supplies, but again, 80 bucks, you could spend $20 on a good set of leads from Pomona or something. Alright, let's dig straight into the guts of this thing. I'm going to power that off, and oh, it takes a second. Alright. Let us start poking in the guts of this thing. Alright, we got a bunch of screws around the sides. I guess let's get into it. Does this fit? Yes, it does. Interesting. Okay, so the plastic has self-tapping screws, which is a minus on its quality of construction front. Self-tapping screws in plastic are kind of easy to screw up, and not really reasonable to recover from. Give me a second. Alrighty. There we go. So the let's look at the way it was constructed first. You got a symmetrical steel outer cover. So definitely designed to a cost. This is symmetrical on... Actually, no, it's not symmetrical. These holes are spaced out differently on each side. Either way, super easy stamping lid. And in terms of thickness, it's... What is that? It's kind of like a 20 gauge steel. It's durable enough. Now let's look at the power supply. I'm going to use something at least kind of insulated while I'm poking around in here. So, fan. We got, oh, my stupid head getting in the shot. Alright, and that's also overexposed. So let's knock that down a notch. Alright. You know what I can actually do is I can enhance. No, wrong enhance. Actually, no, that is the right enhance. I just want to do that. Good enough for government job? Alright. What do we got? From my left, actually no, the camera's left as well. AC input module with what looks like no EMI filter, so again designed to a cost. AC 110 volt selector switch is really just an on-off switch. With a surprising thickness to this lead, so I'm actually wondering whether or not the mains voltage actually passes through here. We have mains voltage through a not very well controlled set of leads, so on assembly this could get pinched in the casing. Going to the on-off switch, they do seem to switch both hot and neutral together on this power switch, so when you switch it off, the entire board no longer touches either hot or neutral AC. However, the ground is always grounded, so that's good. The fan does go to a this connector, as is. Okay, so all of the leads going onto this board can be disconnected. That's at least good. Switch mode power supply transformer. A couple big surface mount resistors in there. What look like a couple of diodes. No, these are transistors. Component markings Q2 and Q3. And then this big Q1. What's interesting is that one of these is gate, if it's a MOSFET. But they've got two 150 ohm resistors across. Oh, wait a second, that's capacitively decoupled, so what's a TO247 layout? I've just got to remind myself. TO247 MOSFETs. Interesting. Okay, so TO247 MOSFETs tend to be gate, drain, and source. So why does this gate have a 150 ohm and a capacitor to gate? Weird. Also, capacitive coupling to ground. That's kind of strange. It looks like this is the input filtering stage. You've got AC voltage in, what looks like it's a negative temperature coefficient polyfuse. Got a couple capacitors, EMI filter. So this is the EMI filtering stage. What looks to be a full wave rectifier. So this takes your 110 and turns it into DC peak to peak. What is that? 110 times 1.414 is 155 volts? It's probably closer to 170 volts. If it's 120. Whatever it actually is, it's around that much voltage. At least that, if not a doubler, applied somewhere in here as well. I don't see any diodes for a doubler, because these two are marked as transistors, which is strange because normally a switch mode has two sets of additional diodes and a curious. Also, the MOSFET is electrically isolated from the heatsink mounting plate, while these two diodes aren't. Well, these two transistors are not, and I'm curious what they're for. Further down into here, it looks like we've got at least one of these is a bootstrap power supply. The way switch mode power supplies work is they need a bootstrap power supply to take 110 into 5 volt logic for the rest of this board, so that the 5 volt logic actually starts up and then can start working the main power supply. Looks like this is the output filtering stage, and there's the outputs. You've got 2 shunt resistors, which is kind of curious. Yeah, okay, so this is the negative side, because you see the negative markings on the, oh, it's a little overexposed. Wow, the dynamic range on this camera is arse. Negative marking on the capacitor, so this is the negative rail. So you get 2 shunt resistors before you go to the negative, and positive just goes straight there. So they're doing low side shunt resistance, or shunt measurement with 2 resistors. Why are they doing that? That is strange. Okay, beats me. But continuing on, these 2 transformers, I'm not sure why they're 2, because I'd only expect a very low-key bootstrap section here. And just from the layout of the board and where the AC voltage is going, I think this right here is the bootstrap, because you've got something directly connected to the full wave rectifier. Oh, my head's in the way. Full wave rectifier directly connected to all of these pads on this chip. And that chip is a TNY277GN? Let's look that up. TYN? TNY277. I think. And Mauser.ca TNY277 datasheet, $1.67 a piece. Power Integrations Tiny Switch 3 family, offline switcher, enhanced flexibility and extended power range. Yep. It looks like that is our bootstrap, and the typical layout I'm just trying to read this data sheet real quick. The typical application. Okay, so the tiny switch is effectively the MOSFET that uses this transformer here. Center tapped on primary. Oh no, not center tapped on primary, and then 2 secondaries. One of the secondary windings is used to power that, which is strange, and I don't like to understand bootstrap power supplies, they're confusing. And the other secondary goes to the rest of it. So okay, yeah, that's a bootstrap right there. And it does look pretty consistent because you got this white outline indicating the live AC section. So, yeah, let's keep going. I'm going to nerd out about everything here. Let's open that aperture back up. Alright, we got the front panel, this wanptech.com silk screening. You've got, let's see, connections here, VGA, GC, L minus G plus AV RG. That is interesting. Alright, we got a display driver, because these just go to the pins on the 7-segment displays. We've got a Nuvoton chip. Interesting, we've got a couple of what look to be small linear power regulators for the circuitry on board here. So it looks like they're taking literally whatever the voltage output is from here and just feeding this board. They got an unpopulated output connection here too, which is kind of neat to see. Yeah, I don't really feel like taking this apart further, but I could. Inquiring minds want to know what those chips are in the back. Interesting. Okay. So I remember seeing this in an EEV blog video a while back, where there was a power supply that didn't do. It had a temperature measurement on it. I think it was a wireless control unit and a power supply module, but the wireless unit displayed the temperature, but Dave Jones couldn't find the what's it called, the thermistor or something. But I suspected at the time that they were doing temperature sensing by voltage drop over a diode. And what do we have here? We've got a D1 diode, and just in there, you can just make it out, is a small signal diode. It's probably like a 1N4148 or something similar. There are these instruments in analytical chemistry known as high-performance liquid chromatography instruments. They tend to do leak sensing by one of two means. Either, sorry, I guess taking a step back, these instruments use pumps to move solvents around, and basically you have fittings that are either tightened by hand or by wrenches, and if they leak, you want to know whether they're leaking so the instrument doesn't just dump a bunch of flammable solvent all over the place. They either do leak sensing by total internal reflection, so you've got a beam of like IR light going into a device, and you're expecting a certain amount of IR to come back the other way based on the total internal reflection on the business end of the glass rod. In the event that you get like a droplet of liquid or whatever, it clumps on the end, and that changes its total internal reflection, which means you end up changing the amount of IR, and it knows that there's a leak. The other way of doing it is they have a little diode, and that little diode senses what the temperature is. So if you get a little drop of liquid on a warm diode, its forward voltage drop changes, and you end up sensing that there's a temperature drop, and that means that there's a leak. Okay. And I think my stream might have died. Maybe. One second while I troubleshoot this technical difficulty, because normally it doesn't happen. Alright, it looks like I'm back. I think. It just decided to stop working for a minute. Okay, so I have a couple choices. I could either go deeper into this, or I could stop here. I kind of want to go deeper, but I'm also lazy and I want to go do other things. Oh yeah, for all you folks out there, yes, I will peel off the film for you. Even though I normally don't do that for myself. Yeah, this thing's definitely built to a price. You get the pots. What's interesting is they separated these out. So I'm just trying to trace the paths here. So it looks like they're taking the sum of these two potentiometers for current, and that goes from A to R. The voltage, same thing, they're taking the voltage sum, and that goes from trace might be on the other side of the board. R to G. No, it's on the other side. I can't get to it without disassembling this all the way down to the nuts and bolts, and I really don't want to. I am curious what this TM1640 chip is. TM1460. TM1460. Is that right? 1640. The TM1460 is a John Deere tractor. The TM1640 is an LED controller designed for 128 LEDs max. What? I'm on the datasheet. What kind of driver chip is this? It's by Titan Micro. It's a 2-line serial interface with a clock and data in, and it supports a whole bunch of output pins. Interesting. So this chip actually supports driving multiple 7-segment displays by paralleling, I guess, the different segments. Segment pins are on this side and at the bottom on this side. So segments 1 through 6, 7, and 8 on the bottom 2 pins here, and then different, I guess, almost like a select on the other sides. Interesting. They've also got trim pots here, so you could actually trim this yourself out if you didn't find it was accurate enough, but it seemed pretty accurate out of the box. Best not mess with those. So I guess, how are they getting the data lines for this? Clock. C is probably clock. L, I don't know what that is, but it's probably, L is probably data. I don't have an oscilloscope, so I can't really probe around with it, but the actual display module itself is digital. So in theory, you could take the digital out and take the data from it, run it to an ESP or something. Yeah, it's got some hack potential. Other than that, straightforward enough. I'm really curious to see this fan spin, but I'm not going to do that without getting this output really hot. So I think that's about it for this teardown and review. Seems like it's a decently constructed power supply for its cost of $80. I mean, I remember paying like $200 for my linear that's off screen. I expect this is going to be noisier than a linear, but at the same time, if I don't need anything particularly precise or low ripple, say it's for logic or just driving LEDs, big whoop, 30 volts, 10 amps, drives a lot of LEDs. We'll just have to see how this thing gets on after like some actual real world use. So I think that's it for today. I'm gonna kill the stream. So thanks for watching if you have, or if you're watching this in the future. Let me know what other kind of videos you want to see, because I do electronic stuff, I do airsoft stuff, and kind of everything in between. Let's get this focus and zoom back to normal before I kill the stream. Yeah, it looks about right. Yeah. Alright, that's it for today. Peace.